The life of a SystemVerilog variable. Abstract. The life of a SystemVerilog variable may seem like a mundane topic, but there are nuances that get overlooked, leading to issues that are difficult to debug. Some of the most common issues are how and when variables get initialized, how concurrent threads interaction with the same variable, and how certain variable lifetimes interact with other SystemVerilog features in terms of performance consideration. This paper presents a background on a different categories of variable lifetimes and what their intended use models are, and how improper uses can be corrected. Chapter 1 Introduction. What exactly is a variable? Believe it or not, this is the number one most difficult concept for people when learning Verilog and now SystemVerilog. When Verilog was created as a hardware description language (HDL), it introduced the keyword concept of wires and legs. A wire is a name, the network of connections between the driver and receivers with no storage implied. A, a, a reg does not, leg does imply some kind of storage, hence reg is short for registers. The key difference between them is how they are assigned values. The driver of a wire is a process continuously applying a value with a rules for a resolution when these are multiple drivers. Reg gets each value from a procedural statement and holds that value until the next procedural assignment. The last assignment determines the current values of the register. As the synthesis tool evolved, a reg, reg, reg become to be used more than just for hardware storage, and a more likely software concept for a concept of a variable simply applies to hold a value for later use. Verilog 2001 began to remove the hardware register terminology and replaced it with a variable. Then the SystemVerilog replaces the origin leg with a logic. But there is still no concept of distinctive lifetime for the HDL and the object they describe. The hardware exists for the life of the device and cannot be created and destroyed while operational. For example, field programmable gate array FPGAs for most part of are programmable while in operation. They must be set up or burned in before becoming operational. Okay, B. What is the lifetime? In software language, lifetime is defined by when and from where a variable is available for access. This is particularly important when there are multiple process threads with lifetimes of their own trying to access the same variable. A variable becomes a symbolic name for a particular range of memory locations allocated to a specific data type. Some languages like C or C++ let you see and manipulating the actual memory address associated with a variable in the form of their pointers. Like C and C++, but the SystemVerilog does not. It has the concept of safe pointers which prevent you from accessing memory that does not belong to you or has been reclaimed for other use. This memory safety features is like what exists in the other programming languages just like Java or Go. The most basic form of the variable lifetime is kind of from the hardware design where everything always exists. This is what called the static lifetime. Static variables exist from the beginning of a time when they get initialized to the end of time. I will discuss what the beginning of time means in the next section. All other forms of variable lifetimes involve the execution of procedural code which involve the deeper understanding of scopes, like those introduced by the task and functions and other named blocks, As the SystemVerilog is intended for both design and verification, and must blend hardware and software concepts together within the same language. This becomes especially important as verification test benches typically cross-prove into variables within the design. Understanding when variables get initialized and when they are accessible from other scope becomes critical. Chapter 2 Variable Declaration and Namespaces. Static variables and scopes. A namespace or scope is a region of code where all user-defined identifier must be unique. There are a few different namespaces in SystemVerilog, but we only need to look at regions where variables can be declared. The most basic scope is the module namespace, which is really all design elements including module, interface, package, program, and checker constructs. This namespace is the scope inside which each design element where we can declare variable, data types, procedures, and other structures concepts. For the purposes of discussing variable lifetimes, we can stick to the module construct as there is no conceptual difference with other design elements. Another basic concept is the block namespace which nests inside other design elements. Blocks are typically introduced by procedural code like tasks, functions, and user-defined types like structures and classes. There is also a scope outside the declaration of a design element called the compilation unique scope namespace where a variable may be declared. This is only useful for a small description because as you increase the size of your code, then collisions are more likely to occur. When we declare variables at the top level of the any module namespace, we are declaring variables with static lifetimes. Static implies allocation as part of the elaboration step before simulation begins until the end of simulation time. Elaboration is a process of bringing together all the design elements that make up a simulation environment, replicating and making connections as needed. After design elaboration, simulation is ready to start at time 0. In figure 1, module X and Y import the variable A from the package P. Module Y initiated the module X twice, creating the two modules of static variables B with the hierarchy name, hierarchy path name, y dot m1.b and y dot m2.b. Module Y contains another variable with the same name B, which is allowed because it is inside a different namespace. Note that although the variable A in package P gets imported multiple times, there is still only one allocation of a variable that remains inside the package. Imports do not create multiple instances of a package, they only omit reference to the name. So in the example, there is one variable named A and three variables named B. These variables are heavily initialized associated with their declaration to show a problem called the static initialization order fiasco. So the occurs because all static variables get initialized at a time 0, but there is no way to predict their order of execution. There's a 24 possibilities. One way to avoid this problem is not initializing static variables with dependence on other static variables instead of assigning them within procedural code. Another option that is useful when dealing with a static class variable initialization is called construct on the first use. Instead of accessing a static variable directly, we call a static function which checks to see if the variable is initialized and if the function initializes it if not already. That way it always returns an returns an initialized variables value. B. Automatic variables and procedural blocks. Automatic lifetimes are always associated with the execution of the procedural blocks of code. A procedural scope gets introduced by the begin and or fork join construct or by a task or function. Allocation and initialization commands upon procedural entry to scope and the variable life ends upon exit of that scope. Because initial version of Verilog only had the concept of a static lifetime, the automatic keyword is needed to explicitly declare variables with that lifetime. So in figure 2, there are 5 variables named A with a different lifetime declared implicitly or explicitly. Note that static variables can always be referenced from outside their scope using a name hierarchical path, but automatic variables can only be referenced from within their procedural scope. Like this, figure 2. And the variables declared with the automatic lifetimes can also include initialization, but a special rule exists to avoid problems with the SystemVerilog default static lifetime, which is opposite of the most other programming languages. This shows up most often the loop initialization, where you expect the initialization to occur every time you enter the block code. But instead it only happens once at times 0 as shown in figure 3. You are not allowed to add an initialization to a variable inside the procedural block whose lifetime is implicitly static. There are several solutions to this problem that can achieve your intent shown in the same figure. Two places where the default variable lifetime is automatic are in the declaration of a procedural for loop and a variable is declared inside a class method. Changing the default lifetime for this construction is possible since there are no backward compatibility issues with Verilog. A nuance to the end of the life of automatic variables comes into play when dealing with the concurrent processes created using the fork construct. A scope life gets extended to include the life of any nested concurrent process. In figure 4, the loop variable vi is implicitly declared with an automatic lifetime. The unnamed block declares the variable vj with an automatic lifetime, and it gets initialized with the current value of the vi. Since there are 2 iterations of the for loop, 2 allocations and an initialization of vj occur with the values 0 and 1 respectively. Since processes spawned by a fork and join known block do not start execution until the parent process blocks will terminate, the 2 processes contained in the display statement do not start executing until after the loop variable vi reached to an initial block terminates. However, the automatic variable vi and the 2 copies of vj remain until the 2 display statements finish. Chapter 3, the data types with the dynamic element. By now, we have covered the basic operation of static and automatic variables. Certain data types introduce another dimension to lifetime. These are the automatically sized arrays and classes. Class objects will be covered in the next section. These dynamic data types have in common the ability to allocate or deallocate storage based on a procedural assignment or method call. SystemVerilog provides 3 different kinds of dynamically sized unpacked arrays. So the unpacked arrays aggregate of the dynamically typed elements. As with any variable, all elements associated with the dynamically sized types are removed when the life of the variable ends. A. Dynamic arrays. Dynamic arrays are simply a continuous range of array elements where the range can be resized by an assignment. Resizing a dynamic array might involve copying all existing elements to a new space regardless of what the new array size is increased or reduced. Typically, you size a dynamic array once at the beginning of each lifetime instead of having to use a fixed size array whose size must be determined at elaboration. Its elements are indexed starting with the integer 0. This is the most efficient way of accessing the block memory, and especially when needed to access the entire array. Note that the distinction in the use of the square brackets in figure 5 with the square brackets to allocate a dynamic array versus the parenthesis of a class construct new. Queues. When using a queue, you typically access only the head of a tail element and repeatedly deleting one element at a time from the head or tail using the push or pop method. A queue is implemented as a linked list, which makes the head and tail access very simple. But this comes at the expense of taking up more memory for each element and requires a traversal of elements to get to an element in between the head and tail. As with any unpacked array, you can copy an entire queue from another array or from an array literal as shown in figure 6. The queue gets resized to accommodate the new array size. Then the initial block ends at time 10. The life of a QA ends along with all its elements. C. Associative arrays. Each element on associative array gets allocated as you access them. There is a lot more overhead for creation of an associative array versus the same size dynamic array. And since elements of an associative array are not always in a contiguous block of memory, there is a red in accessing each element. That is, must check if the element is allocated, and then where is it located. A benefit of associative array is since each element gets allocated individually, you don't need to allocate a contiguous set of array elements. This is useful when you only plan to access a relatively few sparse elements of a memory address space. However, it plans to write to most of the elements. A dynamic array would be more efficient. Another benefit is that you don't have to use an integer as an index to each element. You can associate any type of key, like a string or a class handle to access each element. In the example, figure 7, AA is an associative array with a maximum of 256 elements. The assignment pattern with the default value is used with the declaration initialization to indicate the value returned for any uninitialized element. The first reference to AA4 is the FFFF without allocating element 4 until the following assignment statement. Associative arrays cannot be copied from other arrays unless they are associative with the same index type. D. Arrays of arrays. One thing that may be unfamiliar to some users is that SystemVerilog does not really have multi-dimensional arrays. It has arrays of arrays. You can declare a one-dimensional array of any type, and that type can be different kind of array of another type. In figure 8, DQ is a static variable whose data is a dynamic array of queues of bytes. The new 5 operator allocates 5 empty queues and nested for each repeated loops allocate 1 queue element to DQ0, 2 queue element to the DQ1, and etc. When the loops finish, each element of first dimension will have a different number of elements for each second dimension. The total number of bytes in the array is 1 plus 2 plus 3 plus 4 plus n equals 15. The last statement copies the 4-element queues in DQ4 to DQ0, and erasing one element queue that was in DQ0, the total number of bytes goes up to 18. Figure 8. The E, the class object with dynamic memory management. Class objects are a special case of dynamic lifetimes with some important distinction. Comparable to the dynamically sized array, the class object creation is accomplished through the procedural call to a new constructor method. However, access to that object is always through an indirect reference called a handle. The handle can be stored in multiple variables that are all referenced the same the same object. The consequence is that there is no specific procedure statement that destroys the class object. SystemVerilog automatically keeps the track of all variables referencing an object and deletes that object after no references to it remains. How soon after is not observable to the user since there are no remaining references to it. A class variable can have kind of lifetime static, automatic, dynamic as an element of an array, or dynamic as a member, another class object. The variable lifetime indirectly influences the lifetime of the object by determining when the reference to the object can be removed. The D module inside of figure 9 defines the class C containing one object packet, which is a dynamic array. The construct of the class takes one argument that allocates a packet array to the desired side and randomizes the package values. The module defines a static class variable h that can initialize with a handle to object returned by constructor. The constructor allocates the packet array with two elements. The initial block calls the run1 function 5 times. Each call to the run allocates the automatic variables. Temp gets initialized with a handle to an object with a 3-element packet. It then copies the packet those handlers was passed into a task into a newly created object, so the 3-element packet gets replaced with a 2-element packet. When executing run1, the life of the temp variables ends. The only reference to the object just created disappears. Next, the run2 function gets called 5 times. The only difference between the run1 and run2 is that before the run2 exists. The handle that is stored in temp gets pushed into a static queue list. Even though the lifetime of the variable's temp ends, the reference to the newly created object remains as an element of the list queue. At the end of this simulation, there are 6 class object references. One is the static variable h and 5 different references in each element of the static queue list. By keeping track of the all reference to objects until there are no longer needed, SystemVerilog ensures that every reference is a safe reference to validate the object. This consequences of this is the user is still tasked with removing the references when they are no longer needed, otherwise they can be personalized with memory leaks. 4. Subroutine lifetimes. The lifetime of a function or a task is a concept peculiar to the Verilog. The initial version of Verilog started out having only static lifetimes of functions or tasks, meaning that there was no core stack for arguments or variables local to subroutine. This meant you could not have recursive or reentrance routines, unlike most other modern programming languages. The original reasoning was that synthesis could not create stacks of memory dynamically when called. SystemVerilog 2001 added the automatic lifetime qualifier to give routine the normal behavior of most programming languages. SystemVerilog added lifetime qualified for modules and interfaces so that the routines defined in that module would be considered automatic by default. But you didn't have to add an automatic keyword after each function or a task declaration. Now the lifetime of a class method is always automatic. You cannot declare them with the static lifetime. This is not to be confused with the static class qualifier, where the static keyword appears to the left of a function or a task. This means that it is a method of a class type, not of a class instance of an object. Figure 10 shows the function factorial with a static lifetime and a static argument n when first called with entry, and recursively called factorial 2 and then a factorial 1, and the one static variable n is set to 1, and the return value incorrectly becomes 1 star 1 star 1 is equal 1. The solution for this is declaring the module automatic or function automatic. Then each core gets a new instance of automatic variables n, and the result becomes 1 star 2 star 3 is 6. Okay, the chapter 5 is summary. This paper has shown various interactions between name, scope, and variable lifetimes. It provided guidance on how the different types allocate memory and consequences for choosing one type over another. It also shows several examples of coding errors because of misunderstanding variable lifetimes, and it gave tips to avoid them. Okay, today I read this paper, the life of SystemVerilog variables from 2021, DVCON2021. Okay, thank you for your time. See you next time.